Yeah, hi, I'm the TA of this class, Minje, and today I'm gonna proceed the practice session on recurrent neural network. And this is week 9. And the theoretical or core part of the recurrent neural network was already covered by Edward Choi. So in this practice session we'll focus on the implementing the neural network, but with Torch package. And this is the table of contents today. First, we'll cover RNN, and then GRU and padding. And next part is sequence to sequence model with attention, and you will manually implement the decoder with attention part, but other parts are already implemented. And these are the reference you can study more. By the way, this part is for processing the input or sequence in a batch-wise manner. So there is already convenient tool like Hugging Face tokenizer, but this is not transformer session. So we will manually pre-process the padding, pre-process the input with padding. Yeah. First, let me mute the other guys. Okay. This material was already given to you guys, right? And just download it and open it in the Colab. So first part, implement RNN and GRU. Please import required packages like torch and torch.neural network, torch.neural network.functional by simply putting the shift enter. Oops. Yeah. And this is mathematical core mathematical form of recurrent neural network. It describes how RNN works or operates. So before we start, let's implement the simple RNN. There is blank like this. You should implement 6 lines of code, and I will briefly cover this matrix multiplication form of like first in RNN structure there are like metrics for how can I say, processing the hidden state to hidden state and input to hidden state. So these are metrics for both respectively, W and H. And after that, you will sum these two and it will go into the nonlinear activation function like 10H. Then additionally, you can add the output linear function like V. And if you want to do something like classification, then you can put the OT vector into softmax layer. And this W, U, V, and H, O, Y are all described in this matrix multiplication form or equations. So what you should do is all, that's all. It's all you should do. So let's get started, and I will give you 15 minutes, because we will put more time into implementing RNN from bottom like this, and we'll implement the RNN and GRU class with internal package, with Torch internal package, and then we will manually implement the attention mechanism in the decoder module. So I will give you only 50 minutes or 50 minutes, yeah. And if you have any question, please ask in the chat box. Oh, first, I will give you the link again. And the linear. And 소영 asked that in these equations, how can I implement the B and C like bias term? Your question is this, right? Did I get your question in the right way? If there are already, if you initialize the NN dot linear, or let me show. There would be already it. You can check that NN dot linear. If you initialize the NN dot linear layer, then it has a weight property, and oh, this is 4 by 3 matrix, and in many cases, if you initialize some neural network layer, then the torch package automatically gives you the bias term. Yeah, as far as I know. Maybe you can control whether if you want to if you want not to implement the bias term, then you can control that by input the argument like this or this. Yeah. Oh, okay. Oh, sorry. What? Okay. Okay. This is the solution, and I will give an explanation on it. First one, W is for mapping the hidden state vector, mapping the hidden state vector to hidden state vector in next step, right? Next time step. Previous hidden state vector from previous time step to next time step, and this is for mapping between the hidden state vector, and this is for mapping from input vector to hidden state vector. And last one, V is for making output, a linear layer for making output. Then we can get the probability with and the log softmax function. Then this is how we'll forward the input vector with matrix multiplication. Because we mapping the hidden vector to another hidden vector, it is what is square. We have square matrix. The self.w linear matrix is like square matrix, which has dimension hidden dim comma hidden dim by hidden dim, and this is for mapping input to hidden state vector. So it has input. It has a dimensionality of input by input dimension by hidden dimension, and you can freely choose the output size in this single cell from the bottom, single cell for implementing from the bottom. But in PyTorch.NN package, output has same dimension with hidden dimension. Anyway, you can freely choose output size, and you can map the hidden dimension into output vector with a fixed output size, and then it'll gonna proceed into the softmax function. So this W is this W, and this U is this matrix U, and after the input and previous time step hidden vector go into the W and U matrix multiplication, and then output the A vector, and this A vector goes into nonlinear activation function like 10H. And this line of codes describe this matrix multiplication equation, and then V works, and it outputs OT, output for time step T. Then by using O, you can get the probability from it, and it return Y and H. So in this case, the input has feature size 3. So this, where is it? This U has input size 3, and H0 has hidden dimension size 4. So these three terms also have value 3. And you can initialize the single RNN cell with input size 3 and hidden size 4 and output size 4. So you already set For example, I already set the output size as 4. So this output size we're gonna have the value of 4. And if the output vector goes into the softmax function, then it will classify the output size with 4 classes. Yeah. But I said it is single RNN cell, and why I said single is this is not recurrent yet, right? Because there is no for loop. There's a single forward, and there is no. If you have if you have long sequence, if you have long sequence, and the RNN single cell should iterate multiple times with the length of sequence, but we only forward for single time. But PyTorch.NN gives you multiple iteration automatically. Yeah. In the following section, we'll learn basic usage of PyTorch RNN layer with some example codes and practices. And if you could if you could write this code by your own, then it would be easy because we'll implement the class with PyTorch.NN package, which already implements the nn.rnn or nn.gru function. And input size, this input size and hidden size, we already covered this input size and hidden size before. And another argument for RNN and GRU layers is unknown layers and bidirectional argument, and the other one is batch first argument. In this RNN single cell, you build the single layer of RNN, but by increasing num layers, like num layers equals to 2 or 3, you can build up you can stack the RNN layers. And if you set the bidirectional argument as true, you can easily implement the bidirectional RNN. And if you set the batch first as true, and the input and output tensors are provided as batch.spatial, the sequence.feature. And we already covered this argument, and it is similar as this explanation. So this is a simple example of RNN with 2 layers. If you run it, you have input X with size 1 by 5 by 3, which means batch size, sequence length feature respectively, and you have initial hidden state vector, because every RNN cell's input consists of input vector and previous hidden state vector. And if you want run the RNN cell at the first place, then you should initialize H0 on your own H0. You can initialize it like 0 vector or random vector. save your initialization or hey initialization. Yeah. And by putting this argument into nn.rnn, and you can initialize this RNN2 instance, then, and by run it, by inputting X and H0 into RNN2 instance, you can get the output a hidden vector. And this is what you got. You can simply run it by putting the shift enter. And this is bidirectional case of RNN. And this is what you have to do. You make your own RNN. And please make your own RNN by changing dimension, input dimension or hidden dimension or number of layers or bidirectional vector. So here, you already implemented the RNN from the bottom, like this, right? So it will be more easier because you will use nn.rnn. So I will give you 5 minutes for it. Yeah. Let's meet again at 11:17, 18. Question, are we implementing vanilla RNN or attention model? Yeah, you can implement attention model, but this fixed structure, maybe it is hard to do it. And we have already additional session for implementing attention model. So maybe implementing vanilla RNN is enough for 5 minutes. Okay. When you implement this class and method, each method and set the properties, maybe it would be better to refer this initialization or instantiation line of code. And I should have told you before anyway. Set the argument as a self dot with self dot something. So set the property from the argument with this clause, and you can initialize the NN.RNN internal RNN module in PyTorch.nn package with the many arguments you already inputs. And previously, in single cell of RNN case, you already implement the output layer that maps the hidden state vector to output vector. But in NN.RNN module, there is no another linear layer for mapping the hidden state vector to output vector. So you have to add a line of code for output fully connected layer like this, and it will map the hidden size multiply num directions, which can be 1 or 2 to output size, right? And next part is GRU, but as you already know, it has 2 gates and it is less than 3 gates, which it has less gates than LSTM, which has 3 gates, because in GRU case it delays the redundant parts of gate, so it can train the data faster than LSTM usually, and it has almost same arguments as RNN we already saw, and the detailed explanation and default values are available on the official site pytorch.org. And if you did well on previous RNN implementation, you can simply change the NN.RNN to NN.GRU, because NN.RNN and NN.GRU share the arguments, as I already said. So I will give you 5 minutes again, and if you didn't complete the previous RNN class implementation, then keep on it. And if you did it already, then the control then copy the RNN class and paste to this part, paste it into this part, and change the RNN to GRU. Okay, Han, can you show the bidirectional RNN code, please? Okay. Okay. You want this part or this one? By the way, as I already said, but it can be confusing. This can be confusing. Because in the case of single RNN cell, we already implemented at the first place. It proceeds a single iteration, but in NN.RNN module, if you input the sequence length, then NN.RNN automatically proceeds the length, the times of lengths, sequence lengths. I mean, it fully goes into the iteration of n times, max length time. So you should pick the last hidden state vector from output, right? Output from RNN. Because you want to classify or something the last hidden state vector into something, right? So this -1 is for choosing the last hidden state vector. 그러니까 영어로 제대로 말했는지 몰라서 한국말로 다시 설명을 드리면 저희가 처음 싱글 RNN 셀을 만들었을 때는 RNN이 기본적으로 리커런트 뉴럴 네트워크니까 리커런트면은 같은 걸 계속 다시 써야 되는 거잖아요. 근데 싱글 RNN 셀에서는 한 번만 아이터레이션을 한 번만 돌았단 말이죠. 포워드를. 근데 리커런트 뉴럴 네트워크 취지상 말씀드렸듯이 시퀀스 랭스를 넣었다고 시퀀스를 넣어서 시퀀스 랭스만큼의 어떤 토큰이 있다고 하면은 그 랭스만큼 돌아야 되는 게 맞잖아요. 근데 전에 저희가 싱글 RNN 셀을 할 때는 그 랭스만큼 돌지 않고 한 번만 포워드를 했다는 거고 그 nn. 모듈에 토치.nn 패키지에 있는 nn.rnn이나 nn.gru를 보면은 그냥 그게 전체 시퀀스만큼 아이터레이션을 알아서 돌게 해놨거든요. 포워드를 하면. 근데 아이터레이션을 그렇게 전체 아이터레이션을 돌고 나서 맥스 랭스 그러니까 랭스만큼의 시퀀스 랭스만큼의 벡터가 있을 거니까 그 벡터 중에 가장 마지막 히든 스테이트 벡터를 고르고 싶어가지고 -1을 넣었다는 소리입니다. 그래서 그걸 가지고 뭐 풀리 커넥티드 레이어에 넣어가지고 소프트맥스 레이어 거친 다음에 그 가질 수 있는 경우의 수에 대해서 프로버빌리티를 분배를 하고 그걸로 뭐 의사결정을 하고 이런 식으로 진행이 된다고 이해하시면 될 것 같아요. Okay, this is GRU class part, and everything is same except for this f.gru and n.gru part. And instead of the input and hidden state vector, the hidden state vector at time step 0 into forwards input that hidden state vector and input to what? Input vector to RNN cell. You can input the both two vectors into GRU cell, which is already implemented in torch.nn package. And that's all. And everything else is same. And you can run your own GRU. Oh. You can freely set the bidirectional argument as false, and this is my own GRU setting. But you can arbitrarily choose any kind of argument. But yeah. Because RNN inherently, the inductive bias of RNN is the input has some orders, right? And you will process it sequentially, and that's the inductive bias of RNN, unlike the transformer model. And because of that, it inherently has the defect like gradient vanishing, and the impact or effect of initial hidden state vector or the hidden state vectors on early stage will decrease as the time step increases. So if you set the sequence length like 1,000 or something, if this sequence length argument is way too large, then the RNN structure cannot properly process or encode the sequence because of the inductive bias and internal defect of the structure. But anyway, you can choose it. You can set any kinds of arguments. And third part is padding. We can make better use of the GPU by training on batches on many sequences at once, but doing so brings up the question of how to deal with sequences of variable lengths. The simple solution is to pad the shorter sentences with some padding symbol, in this case 0. And there is another way of processing the input in a batch-wise manner. Another way is like truncation. If you have longer sequence than max length, then you can cut or truncate the remaining part. And if you have shorter sequence than max length, then you can fill the blank with the paddings. And this part is for letter 1. Explain the letter 1. And as I already said, for example, in Hugging Face tokenizer module or package, you can easily and automatically pad or truncate the input that can be utilized in a batch-wise manner. So, but in this part, we're gonna use RNN, so you should manually process this. Okay. Import the packages and get the data set. This is IMDb data set, and there is lots of pairs of review and positive or negative label. So if some guy wrote the review, then it has positive sentiment or negative sentiment. So the review contents and the sentiment correspond to this review and labels respectively. And open it. You can check the short example of it and preprocess the reviews to process it or run it with RNN. And this count word means in the data set, for example, the word the, there are around 1,000 of word the and 600 of 500 of this, and so on. And you have to map this kind of word, natural language word, into some index. And we say it made the book. We said this process is making vocab, and the vocab index 1 means the word the, and vocab index 2 means the word and so on. And then set the encoded labels and change input to index. Return features of it. And you can, this is what you have to do. Please make the padded feature function. The input is reviews int. I mean the review index of the review, and sequence length. Yeah. I will give you I can give you only 5 minutes for it. After inputting the review into this function, this function should or processed input should have the form, which is optimized at processing in batchwise manner. By padding it, all batches have same length. Okay. Yeah, I think this is quite. This is just pre-processing part, and there is no literally deep learning things. It is rather like algorithmic algorithm or what, data structure things. So let me explain it briefly. For all reviews in the reviews end, if the review length, the length of review is shorter than sequence length you set, or sequence length you already set, then initialize the zero heading and add the zero heading to the review. On the other hand, if the length of the review is larger than sequence length, then you can cut it. Cut the remaining remaining part off. So by indexing this 0 to sequence length for review, then you can get a new sequence of review. Then you can change the data type of new sequence with the NP.array, NumPy array, I mean. Then this is the whole process of padding features. This is maybe core part of pre-processing. And then split the data into train and test data. Then this is for checking the statistics of input data. Then you can initialize the sentiment LSTM for classifying the sentiment of reviews by simply put the run button. Then you can train the model. You can train this initialized instanced sentiments LSTM instance, right? But you have to add 1 to length of vocab to int instance, because you have pad for processing the input, right? You already added the pad into input, but that pad is not originally not in the original text, review text. So you have to add 1 for the pad token. Then after setting the vocab size and many other arguments, you can run the training pipeline. But this is simple application, and PyTorch.organization, in the site of PyTorch.organization, you can get the detailed explanation on it. So you can simply train and evaluate this pipeline. Yeah, second part is sequence model with attention. And this part also needs the pre-processing, but this course is not about the pre-processing, so I will simply run the pre-process code. Yeah, it's not. Yeah, basically, and this is a core part, and you will implement this part. Some guys already asked about the attention model. So if you want a brief, detailed explanation, the encoder decoder attention, you can simply refer the or read the neural machine translation by jointly learning to align and translate paper, which was written by Badano and Kyunghyun Cho and Yosha Benjo. And I already gave you the link. And the encoder, the first one is encoder part. The encoder of sector-sequence network is a GRU that outputs, there is a typo, that outputs some value for every word from the input sentence. For every input word, the encoder outputs a vector and a hidden state and uses the hidden state vector for the next input word. But the thing is, this structure, this encoder decoder structure has attention module, and you will implement this attention weight. This decoder is another GRU that takes the output vectors like this, and by using the decoder hidden vector and encoder outputs, you already encoded with this structure. Oh, you can run the attention model, but there is blank here. So what you have to do is implementing this code. By implementing this attention weights, you can connect the encode outputs and decoder's hidden state vector, and you can calculate the encode. You can calculate the weight for the decoder output with corresponding encoder output, right? If you have 10 tokens of 10 lengths of 10 tokens of encoder output, then you have to calculate which token is the most closely related to the decoder token, decoder hidden state vector. After that, you have to make the weighted sum vector of the decoder output, right? So the first thing you have to do is calculate the weight, then make the weighted sum vector. And this process can be implemented with these two lines of code. And this is almost end of this session. And if there are any schedule, you can freely go out. Yeah. I will get back in 11:45, 55. Okay, some guys required ask the more explanation on it. Yeah. Actually, this encoder and this decoder will decode the sequence in an autoregressive way, and which means the decoder outputs of specific step will work as the next step's input, right? So while doing that, while the mapping that, for all tokens in encoder outputs, you should calculate the weights, because some token of encoder output has less relation with decoder token, or some token, another token will be highly related with the token. So you have to calculate the weights that reflects the fact that I mentioned. So, and by using that weights, you have to make the weighted sum vector. And by using it, you can complete these sentiment classification module with attention. 그러니까 오토 리그레시브라는 거는 한 스텝의 디코더 한 스텝의 특정 스텝의 디코더 아웃풋이 다음 스텝의 디코더 인풋으로 작동을 한다는 거고, 그 과정에서 우리는 그냥 생으로 그 시퀀싱을 하고 싶은 게 아니라, 시퀀셜리 그냥 리니어만 계속 통과시키고 싶은 게 아니라, 특정 디코더 아웃풋이 어떤 인코더 인풋과 더 관련이 있을지를 고려해서 다음으로 넘어가고 싶단 말이죠. 그게 어텐션인데, 그 어텐션을 하기 위해서는 뭐 예를 들어서 인코더 아웃풋의 센텐스가 총 10토큰이 있다고 하면 10토큰 중에 어떤 게 관련이 있고 어떤 게 관련이 없는지를 가려내야 하니까, 그 가려내는 과정을 지금 attention weights 2 lines of code에 구현하라는 소리고, 그걸 해가지고 이제 sentiment classification 모듈을 만듦으로써 네, 그 attention encoder decoder structure with attention을 완성할 수 있다는 거죠. Okay, I already gave you an answer, and let me explain it briefly. The core part of this line is this hidden, which means the decoder hidden state at the last time step, and the self-attention metrics, which is the parameters for attention, and this encoder output. But by the way, you can choose in this class, we used the attention model with linear layer, but you can, the another options for the attention, there is various options for implementing the attention. And for example, there is dot product attention or something. Then if you choose to use the dot product attention, then this self dot attention matrix with linear layer or and the parameters is useless. Anyway, the core part is the core hidden dimension and attention matrix and encoder outputs. And hidden dimension, this encoder hidden, this encoder hidden vector has the shape with 1 by hidden dimension, because it is this hidden means the last single token of decoder embedded with hidden dimensional space. And that self-dot attention matrix has shape of hidden dim by hidden dim, and thus it is a square matrix. And this is for calculating or storing learning the correlation or a relation between the inputs feature and outputs encoders outputs features and decoders token. So to calculate the weight from between the features, between two feature space, it has shape of hidden dim by hidden dim. And the last one is the encoder output would have a shape of length, comma, hidden dim, but we put the transpose to do matrix multiplication between this and this. And what it means is between two vectors, we can calculate or learn the relation with two vectors with this attention matrix. And by doing so, we at the result, we can get the 1 by max length tensor. And if we input the 1 by max length tensor to the softmax function, we can calculate, we can get the weight of each encoder tokens to the decoder token, right? If there are 10 tokens of encoder outputs, then the weight of first encoder token to decoder output, the weight of second encoder output to decoder token, and so on, and the weight of 10th encoder token to the decoder token. Then each element of this attention weight, this 1 by max length tensor means each element of this tensor means that this relation, right? So by simply putting it into softmax layer, then you can get the probability, which is sum to one vector. And by doing so, we can simply complete the attention model, attention sentiment classification model, right? Yeah. If you complete this model, then by just simply simply run the code for a pipeline and evaluating with evaluate the model with blue score and visualize the attention with the graph 2x2 with two-dimensional graph, two-dimensional matrix. For example, I'm not taking sides and June crane something, and this M and cranes has high relation, right? You can interpret the attention moduli with this kind of graphical visualization. Okay, this is the end of the presentation or practice session. So you can freely leave the session and ask the question. Okay, thanks.